Hello, everyone, and welcome to the show. This is the Geek Narrator podcast. I am Kaivalya Apte, your host, and today I'm joined by Lalit Suresh, CEO of Feldera, and we are going to talk about incremental view maintenance, and we are going to simplify some of the concepts around it. We are going to talk about Feldera, how it solves the problem, why it is a problem, take some real world examples, probably also related with DBSP, the mathematical foundation, and go into deep understanding of how it all works and what exactly does incremental view maintenance even mean. So Lalit, thanks a lot for joining me today. I'm really excited to have you and learn more about Feldera and all the amazing concepts. So welcome, and let's start with a little bit of introduction about yourself, about your background, what you've been currently working on, and also what is the core problem you tried to solve when you created Feldera?
So first of all, yeah, thanks for having me, Kaivalya. It's really great to be here. So my own background is I'm a computer scientist by training. My expertise was distributed systems and networking. I did my PhD from TU Berlin, in fact. So uh, we've been in the same city. I think after my PhD, 2016, I moved to VMware Research, where I joined as a postdoc and then became a senior researcher. And I was working on all kinds of problems around cluster management, performance, systems in general, I would say, right? And during my time there, of course, I was also working with the folks who are now my co-founders, who have been leading this sort of thrust around incremental view maintenance for some time. And it's funny how when they were working on it for the first time, I went to them and were like, guys, this has to be a solved problem, right? Like you have some queries over some data. I thought, materialized views were a thing, and they said, no, it's not, right? I was like, okay, I believe you. I trust them, so I believe them. And eventually, during that time, I was actually building a sort of SQL-based cluster manager, right? So you define your cluster state. Like if in Kubernetes, you would define, your nodes, your pods, all of these as tables in a SQL schema. And then you write views to decide how these things are placed, how these things are scheduled. And of course, I immediately ran into the incremental view maintenance problem there, right? Because most of the time, your data changes are much smaller relative to the overall size of the database, right? And so I obviously went to these guys and be like, okay, let's use the thing that you were building before. And that's kind of my foray into incremental view maintenance myself, right? So as to this project at VMware at the time, Leonid and Mihai, these were these are the two, I would say, leaders behind that effort. They were building a data log based tool. It was called Differential Data Log, which was built on top of Differential Data Flow, which Frank McSherry had developed. Right? And they were using that for actually building sort of these network control plane type of use cases. But eventually, the more we looked inside VMware, the more we found that this problem is everywhere, right? Like people are doing batch compute for problems, which involve periodically recomputing the same things over and over again. And they all tend to have this fundamental property that almost always the size of the changes are very small relative to the whole data set. Right? And so at VMware, these guys applied differential data log to this product called VMware Skyline, where they used to do these 2-day long batch jobs that was just taking observability data from customers and telling them, hey, you have this known misconfiguration in your infrastructure. Don't pick up the phone to call support, go fix it before you do that. That was kind of the model there. And of course, it was not tenable, right? As you get more customers worth of data, these batch jobs are it's actually getting progressively more inefficient because the more data you have, the more of the computation is wasteful in terms of just recomputing the same things, right? They applied ddlog there, and the time to insight went down to seconds, right, per processing a delta. And this is 2,000 queries evaluated in seconds, right? So that was a huge leap. And during this time, while trying to push differential data flow to its limits, these guys kind of ran into limitations that made them go okay, it's time to go back to the drawing board. And that's when DBSP was formed, right? They started looking at it from first principles and turned out that there's a very clean, very clean algebra hiding underneath. I would say there's decades of work that people have been doing in this space, and they had the insight. They wrote the paper, and this twin success of like the research impact of the DBSP paper and the impact inside VMware was basically what made us confident enough to found Feldera.
Okay, sounds good. Thanks for giving the the context and the background. The problem you have explained is probably pretty familiar to everyone, right? Many people who have worked with databases, written SQL queries and tried to run some aggregations and stuff like that. It's very common. And if we talk about like a relational database, I don't know, Postgres. Nowadays, everyone works with materialized views, and you also have Postgres extensions that does it incrementally, and to avoid recomputation, like FCO is there. But I think this problem itself is even more challenging when it comes to distributed systems and stream processing and other data intensive applications, like I don't know, AI or ML workloads and stuff like that. So I want to understand what exactly makes it even more difficult in the context of distributed systems, where there is high volume of data, there is really variety of data, and the velocity of data. All three are really high. Um, uh, and the other aspect that you talked about, the batch processing, and I think I mean I love batch processing as a overall idea, but I've faced some problems there as well. Not just like it runs for a long time, it's not very cost effective, but I think when it fails somewhere in the middle, it's again a problem, right? So I want to understand also how batch processing is still relevant, and where do you see it going? So it's like a two question, like why is it a bigger problem in distributed system, and how relevant is batch processing?
Yeah, so we'll take the first one, right? Like I think the question it's less important that we're dealing with a distributed system than the fact that we're dealing with like high volumes of data, right? And I see this in some along two dimensions. One is what is the overall size of the data set that you're working with, and second is like what is the rate of new changes or events that you're processing, right? Like both of those things actually matter.
Yeah.
So from a performance standpoint, I think like what DBSP promises us, what the math tells us, is that, and this is actually like a hard guarantee when you use Feldera, by the way, is that the amount of work we do when we process a change is one or more inserts, updates, or deletes to one or more input tables. The amount of work we do per step where we process changes is always proportional to the size of the change, not the size of the database, right? So we usually talk in terms of the complexity factors are order k, not order n, right? So the k is much smaller than n. That is kind of the picture to it. So you kind of have to start from that level of fundamentals, right? Like you basically need to know this is what determines how fast Feldera can possibly go, right? Now, if the size of the change is ginormous, like for example, you write some pathological queries where on every input you have to evaluate a full cross product of 1 terabyte size tables, then yeah, like that is the size of the change that we're evaluating. So you'll see that impact, but most often you won't, right? Like most times if you write well-formed queries, you should not. But the guarantee is always the same. The amount of work is proportional to the size of the change, not the size of the database. Now, once you're there is the actual systems components that you also have to care about. Like, so big O notation will only tell you about the scalability of your system. It won't tell you much about the raw performance you get, right? And so here, like DBSP, the engine that we have has been optimized top down for everything from latency to throughput, right? There's a really cool internal structure to how this works, but basically the main determinant of performance at some point is anytime you have joins, distincts, or nonlinear aggregations in DBSP, So for example, min and max are nonlinear aggregations, and by that I mean that you need to keep some history to correctly handle deletes and updates as well.
Mm-hmm.
So when you have these type of things under the covers, we are maintaining indexes. These indexes are LSM trees. And so in a pipeline, when we process changes, you have lookups as well as writes to these LSM trees. That is the systems aspect of what determines our performance, right?
Yeah.
So the architecture internally it's like a shared nothing type of architecture. You have several workers. Right now it's on a single machine. Very soon we'll also have these across machines. The only change that happens then is that some exchange operators will also go over the network. But what we don't do is we don't shard the data flow across machines. Every worker is running a whole copy of the same circuit just for a different subset of the input data. So it's data parallel, not the data flow graph is not split across.
Mm-hmm.
Right. So they're all executing the exact same operation, but on different shards of data, and then you're just sort of blasting through at high speed, right? So the latency matters because the inverse of it in many parts determines individual operator throughputs.
Mm-hmm.
So that's the performance side of it. So we care about both the big O as well as the smaller terms to keep overall performance high. And ultimately, it comes down to some careful balancing between compute, I/O, things like that.
Yeah.
The second question you had asked was about like how this relates to batch processing, right?
Yeah.
I would say batch computing, a la like relational algebra plus SQL from the 70s. In terms of a user experience, it's completely unmatched, right? Look at anyone using Snowflake or Spark, which I would say like these are my sort of benchmarks for a user experience, right? You write whatever complex SQL you want.
Mm.
And people who have no idea about how distributed systems or databases or operating systems work will be able to write these queries, submit them to a cluster. You have thousands of cores and disks wake up, crunch your data, give you back an answer. Like this experience is unmatched, right? And this is where I think like the systems that are stream processors have kind of not succeeded, right? You cannot like forget like the kind of queries people throw at Spark and Snowflake. Like you cannot take much simpler queries and expect the same user experience. And secondly, it's not even the fact that they will not even be able to run many of these queries. It's the fact that even for the queries they run, they don't behave the same way as a batch system anymore, right? So there are, since you mentioned Flink, right? Like there's so many cases where you can actually write a query in Flink and its behavior will look nothing like it would in a batch system. There is no correspondence between the two.
Mm.
So you can't so the semantics are always very ill-defined with things that call themselves stream processors. This is where we want to really differentiate, right? We want to I hold ourselves up to the bar of the batch SQL user experience. You throw whatever SQL at it and it should work. The semantics should be exactly the same as what people are used to. And there I think Feldera has done remarkably well. Right? People literally take like 6,000 line DBT generated blobs of SQL, throw it at us, and they can compare the results with what they get from Spark and Snowflake, and it exactly matches row to row, right? And we're able to do that only because of the theoretical foundation that DBSP affords us. Like we know that we can compile from all of SQL plus extensions down to DBSP, and once we can do that compilation, incrementalizing it automatically is something we get for free from the theory, right? So we are never in doubt that if I have this operator here and that operator there, the result is wrong. We never worry about it. And that's the power of DBSP really, right? Like the compositionality. I'm happy to go deeper into it.
Absolutely.
So this is the unlock really here, right? Like in order to get to that batch experience, you need to be able to guarantee that you can run arbitrarily complex SQL, including recursion, by the way, and give you the exact same semantics that you would in a batch system. So anytime you pause a Feldera pipeline, you look at the state of all the views, right? And you don't even have to pause Feldera, like you can just freeze time, right? and you can inspect the state of the views that we afford.
Hmm.
And it'll be exactly what you would get in a batch system if you ran those queries on static data, the prefix of inputs that Feldera has seen so far, statically, right? It's called strong consistency or atomicity or transactional semantics, if you will. But
Yeah,
we give you that.
pretty impressive. And I like the fact that when it's a proven theory, you gain that confidence that you will have this upper bound. You know the mathematical foundation of it and how it's going to work, right? So that's really powerful. And I want to get into a bit more detail there, just to give our viewers more understanding of the foundational concepts. So you have said DBSP a number of times now, but I
Yeah.
think it's time for us to kind of go a little deeper into what do we even mean by DBSP. We already,
Yeah.
you colored some picture of the architecture, like how it's a shared nothing architecture, and they work on separate partitions and data flow graphs and so on. But let's start from the mathematical foundation of it. What do we mean by that? The theory is there, and how does it relate to the real world operations that we do in stream processing world?
Yeah.
Yeah. So what exactly is DBSP?
So DBSP is a mathematical foundation. It's, to be very precise, it's an algebra on how to compute on streams, right? So yeah, I would draw a parallel to relational algebra. Relational algebra is basically like, so in school we had algebra on sort of integers and stuff like this, right? Like you have some formula, you can use rules like commutativity, associativity, distributivity to basically simplify, solve it. And at any point in time when you're applying these rules, what you're getting out of each of these steps is equivalent to one another, the equal sign that we have, right?
Hmm.
Treating computational problems via this sort of algebras affords you that same power, that you can apply certain rules to sort of rewrite and simplify and optimize the queries and be completely assured that any of these steps is giving you the exact same answer as the original query you started from, right? So relational algebra's real breakthrough back in the 70s was doing this for batch compute, right? Until then, like, it's always important to look at what came before it.
Hmm.
Back then, if you wanted to write the equivalent of a database or some kind of, like, you wanted to store stuff on disk and analyze it, people were basically writing these blobs of programs that actually managed these on disk data structures directly, right? Like, they had to know that here's my format, I have to go here, I have to like jump to another line. Um, this is an index, this is not an index. Like, you had to really be aware of how the data is laid out on disk in order to actually write the equivalent of a query on top,
Hmm.
which meant that when your queries evolve, your representation is going to stop you
Yeah.
from playing, going too far, right? And so relational algebra actually broke that, right? It
Hmm.
basically said, like, you can have a complete separation between what the query is supposed to do for you from how things are laid out and how the engine supports that query. And so with relational algebra, you have some operators like projections, joins, like all of that stuff is defined. And the query is basically like a tree of these operators. It's basically a formula, if you think
Yeah.
about it. And it has certain rules and laws that it obeys, because of which you can actually reason about things like query optimization. It's like, for example, predicate pushdown. It basically says that if you take a filter, you push it before you do the join, it'll become efficient, but it does not change the output you will get.
Hmm.
That's the kind of confidence with which you can apply these rules, because it's not going to break anything, right?
Hmm.
DBSP basically is an algebra for computing on streams, in the same spirit that relational algebra was back in the day for batch compute, right? So what does DBSP say? The beauty of it and the power of it is that it's literally just 4 operators. It's a so-called lift operator, which says if you take a function that applies on a scalar, how do you apply it to a stream, which is you apply it on every element of the stream, like a map.
Hmm.
There's a z-1 operator, as it's called, which basically is what's called a delay operator. And this comes from digital signal processing. And DBSP is a play on words on DSP, which is signal processing. So that's where the inspiration for this comes from.
Yeah.
So it looks at, like, streams of data. right? Like, so you can imagine like 0, 1, 2, 3, 4, whatever, these are streams. The delay operator basically just delays a stream by one time unit, right? Now, out of just this map operator and this delay operator, you can actually start to construct these little circuits which can, given a stream, produce the diffs between elements, right? So that's what we call differentiation. And similarly, the inverse of it, which is integration, which is you kind of, union it, right? So you can take a stream, you can differentiate it, so you get the diffs of the stream. You can integrate it, and you'll recover the original stream. Right? So you can do this, and similarly, you can integrate that, and you basically get the whole history of the stream. Right? You can do these type of things. So out of these two primitive operators, you can now start to construct more and more complex circuits, right? And so DBSP distinguishes between, like I mentioned earlier about linear and non-linear operators. Linear operators are anything that does not require us to keep any state, right? And some, like for example, projections, filtering, none of these actually require you to keep any memory of the history. Because if you think about it, like say I get some rows, I want to know whether, say, where column name equals Lalit, for example, right? I don't need to check any other records. I can check this one record at a time. And I can, if it's an insert, update, or delete, I can decide by only looking at that record whether there's a change to the output.
Right.
Now, things like joins actually require you to keep the state around. And so for a join, for example, let's say you have two sides to the join, right? The left and the right, or A and B, right? What does it mean to compute the delta to a join? It basically means you have to look at the current join. So A cross B, for example. You have to take the delta to one side, see if it appears in the join based on the other side, and vice versa. And the union of these three elements is always the current value of the join, right? And so this is how we apply deltas to a join, right? You check it on one side, you check it on the other side, you keep the history of the last, the previous snapshot of the join. And all of this you can actually recover by just using those little operators I mentioned, right?
Cool.
And the beauty of how joins follow from this sort of algebra and circuits that we have in DBSP is that like this actually recovers what's called the delta join algorithm, right? And that's usually a cool thing in the theory world when you see like one framework actually recovers known good algorithms that people have come up with independently, right? And so it turns out like all of SQL, like of course select where, like select from, filters, all of this stuff is straightforward, but also like joins, unions, distincts, except, intersect, all of that falls out of this. So this is not just relational algebra, but also the extensions to it, like even the sort of windowing functions, all of these are things we can actually recover. From what we know, we are the only engine on the market, for example, that can do sliding window aggregations incrementally. The SQL window operator. Yeah. So hope that
yes. No, I think that that gives a very like a foundational idea of where, like what exactly we are talking about when we say deltas and stream processing and differentiations and stuff like that. And
I can add one more thing there that I wanted to emphasize. So this is just this like the sort of the low level operations and stuff like this, right?
Yeah.
But the real power of DBSP with this algebra is that if you can express a query as a DBSP circuit, like the non-incremental version of it, we have an algorithm that can automatically incrementalize it. And it has no heuristics, so it is not doing any guesswork. It's literally by looking, it's purely syntax directed and mechanical. And that's kind of what enables all of this, because it turns out you can compile from SQL to DBSP circuits, and then there's an algorithm that can automatically incrementalize any DBSP circuit. Okay. And the big power here is that like DBSP is fully compositional. So what that means is if you know how to write an incremental operator for anything here, like for example, a join, how it composes into a larger circuit, like we don't actually have to worry about correctness. The theory is clear that the composition is always correct. And this is what makes it as powerful as it is, the compositionality. Because until then, like the history behind this is that people have figured out how to, like, they take one operator, they know how to incrementalize it, but then how it fits into the rest of the query is unclear. And that's where like there's a lot of complex math and heuristics for very specific types of queries and combinations thereof. But DBSP is surprisingly simple in contrast to what came before it, and has some really cool properties and superpowers that it affords us. Right?
Interesting. I think that the whole idea is really powerful because, first of all, you have very, let's say 4 operators, and they are composable, so you can build more complex. I don't know, should I say graphs, or I think graph is a good word right there.
Yeah, a circuit
Okay.
is basically a graph, of operators.
Okay, interesting. And then it has a very close relation with how like relational algebra also works, in terms of it gives you a beautiful abstraction that as a user you don't have to worry about that, you just worry about the syntax, and then on the background Feldera will take care of optimizing it specifically for your query. And also that is not based out of some heuristics, some metrics based out of data. And I want to go deeper there. Probably we'll take some example and understand how that all happens. um, but let's start with a like a high level architecture, like how things are working. And let's take an example, right? Like I want to take an example from my experience. um, let's say I'm working, I'm a messaging company, right? I support, like, I don't know, chat applications and all types of messaging, not just chat, but also SMS and Gmail and whatever. Like, sorry, email. And I want to provide some analytics on top of it, like how many emails I've sent, how many emails I've I don't know, dropped, stuff like that. How many messages were sent from this channel, from this user. So there's a lot of dimensions happening. There's too many messages sent. So probably we can take some examples from this problem, and try to understand like what exactly is happening when I receive a stream, right? So this is just like, okay, data is coming, but then there is the other part where I want to write some queries, right? And that's when the actual power of DBSP probably is used. So let's take us through this journeys where, okay, data is coming, what exactly is happening at that point, what is the architecture like, and then we can talk about the query part.
Yeah. So the way we put this together into Feldera is that at the outside you basically write tables, like so standard SQL create table statements and then create view statements. And because of DBSP, you can write views over views over views, and you can deeply nest this arbitrarily complex SQL, blah blah blah. All of this is what we call a pipeline. Right? So you can write many different pipelines, and they're completely separate from one another, completely compute isolated from one another. But each individual pipeline, we take the SQL, we run a SQL to DBSP. Like, so we have a SQL compiler based on Apache Calcite. We compile from SQL into DBSP. That becomes kind of our internal representation. We then incrementalize the circuit and then do a lot of optimization passes. There's optimization SQL, optimization DBSP, and eventually we code generate that into a Rust program. Right? So this whole circuit gets spitted out into like a Rust circuit that uses our DBSP library under the covers for the operators. This gets compiled into a binary, and now this binary is your pipeline. Okay. Now this pipeline binary is also linked with some of our crates on what we call adapters or connectors, right? So the DBSP part is completely like, it has no concept of Kafka or anything of where this data comes from, right? That is like that's the outside messy world. And so there's a part to DBSP where we have to turn, like there's a cool thing that we have, and the math requires us to represent data in a data structure that is called a Zset, right? You need this group structure as per the math. And so we represent tables, views, changes to tables, changes to views, and even the on-disk journal as this thing called a Z-set. Right? And the beauty of a Z-set is that it's very symmetric. Like inserts are the same as deletes. It's just a row. Inserts have +1 as a weight. deletes have -1 as a weight. That's it, right? So you can represent multi-sets and sets with Z-sets. The outside world does not talk about Z-sets. Like if you basically do, let's say, select star from something in Postgres, right? What you get is like some rows, but you don't really know the multiplicities of these rows, right? CDC, for example, tells you that something got inserted, deleted. Like there's so many different formats and ways data comes to us. Something has to translate that into Z-sets, and that's basically our connectors. So what happens in your example, let's say one of these create table statements, we might set it up with, let's say, a Kafka input connector, or you push it into us with HTTP. This connector layer inside Feldera that takes this asynchronous outside messy world, gets a payload, has to deserialize and turn that into a Z-set, which is then queued into the Feldera pipeline, like the DBSP based pipeline. The DBSP pipeline operates in what's called steps. It's a synchronous computing model where you take some bunch of changes, inserts, updates, deletes. You run a step of the pipeline, and it outputs all the changes to all the views that it computed in that step. And then it's just really clocking very fast, like it's doing step after step after step, and basically draining this queue of inputs that the connectors have been enqueuing from different data sources, right? So each input table, like each create table statement you have, can have one or more connectors. Different tables can have different sets of connectors. They can all be coming in different shapes and sizes and forms and speeds. All of this ends up into the pipeline through like in this mode, basically, right? Like this connector layer that operates in. And similarly, the views can also emit to output connectors, right? So you can sync the results we compute into some destination. So we take so to your chat example, right? You would probably write some create table statements that have columns that mirror the structure of the payload that we're receiving from some destination, right? This might be some set of columns, it might be some JSON, it can be like, again, there's some schema matching to do.
Yeah.
And then whether you push it into Feldera using our push connectors, or we pull it from things like Kafka or some open table format, etc., it doesn't really matter. Like we don't really care about whether a source is streaming or batch or HTTP or whatnot, right? It's all just some payload that we get that we have to turn it into a Z-set. And once it's in there, it's like a very uniform representation inside Feldera throughout. Yeah.
Okay.
And all these views update incrementally as data comes in.
Okay, interesting.
Yeah.
So let me start from the I don't know, the user's perspective, like the person who is creating those tables, and basically they have to know. Of course, they have to know the structure of the data, right? But they also have to know what kind of queries they are going to run on, right?
Yeah.
And then it's kind of similar to how I would do this in the relational world, for example. So you need to know the table structure, you need to know the queries you want to run, and then you kind of provide this data in terms of tables and materialized views, and then the data is inserted. There is this pipeline that you mentioned. It's basically a Rust binary that takes care of doing this DBSP incremental computation and updating all the tables or the data and the views, right?
And the
That's
views,
what is
exactly.
happening. And when the query is running, it's just taking the data from the views.
Exactly. Yeah.
Okay.
So all of this, like the connectors, the pipeline, all of this is embedded in what we call the tables, the views, the connectors, all of this is embedded in what we call the pipeline. And the pipeline is just a single binary that we run. So for example, in our enterprise offering, that gets packaged into like a container that we run separately, right? From everything else. So if you have like 100 pipelines, you'll have 100 of these containers running in your cluster.
Okay.
Each of them basically doing this loop that I mentioned. Pulling, pushing data, getting data in from pull or push, and then running these steps to update these.
Interesting. Yeah. Before we go even deeper into, first of all, what this Rust binary is doing, and where the LSM trees come into picture and all of that. Again, from the user's perspective, right? Like when I create a table in, let's say, Postgres, and I also know the queries I want to run, I'm also responsible for creating indexes on top of it, right? Like to make it performant. But this part is not existent here, or is it?
That's an excellent question, actually. So we basically take care of all the index. We create the indexes from the queries. So, and that's the main difference from what you would do in Postgres, which is these are ad hoc queries. Postgres does not know in advance the queries you're going to run, which is why you need to define indexes, because you know the queries you want to run. Postgres doesn't, right? Whereas with incremental view maintenance, these are standing queries. These are queries you define upfront. And so there is no ambiguity from our point of view of the indexes we need to keep it, right? So like I said, every time there's a join distinct or a nonlinear aggregation, we keep an index under the covers.
Okay.
Right, and that's what we do. Now there's actually a create index statement in Feldera, and that's for a fairly intriguing reason, because so views in SQL don't have any concept of a primary key, right? Whereas often when people write views and they want to sync it to some destination, like say Postgres, there is a concept of a key there. They know, let's say this is a customer ID, and so I want updates showing up in this view to actually be coalesced into this one customer ID or something like this, right? So we have create index statements to tell our output connectors, and when we attach output connectors to views, what the key should be. Like that's the only scenario where you need it. But all the other stuff, like the performance part of it, is taken care of by Feldera.
Got it. Yep. So it's mainly for the kind of compatibility with the external world, to make sure you have that feature where you can let the user define what they exactly want. Okay, that's interesting. Okay, that's cool. And which means that when I have to, so let's say I'm like evolving product, right? I create tables, I know my queries, but then I cannot guarantee that these are the only queries I'm going to run, right? So I might have to run ad hoc queries as well. So how do I provide that? Do I create like a new view for that, or it is automatically created? How does that work?
We also have ad hoc queries. So when you run a pipeline, you can come in at any time and run ad hoc queries against any tables or views that you choose to materialize. You can run ad hoc queries against, and people usually use this to check whether they have the same answers. We actually use it for differential testing as well, but like people generally use it to like inspect inspect the state of tables while they develop it. Now, you've asked a pretty good question, which is like, how do you evolve these pipelines? How do you evolve the schema? How do you evolve views and stuff like this? Right now, you kind of have to do blue-green updates with Feldera. You write a new pipeline, it has to backfill. Like the new pipeline will have more tables and views or more changes to these, and then we can basically evolve it. We hopefully in maybe 2 weeks, 2 to 3 weeks, we'll actually have it so that you don't need to do that. That is, we'll basically look at the underlying circuit, and we'll find the cut where we can reuse the state from the existing indexes, and so then you just need to sort of backfill whatever's missing, right? Okay. So you can add views, there are fundamental limits to all of this, and there's some trade-offs. For example, say you add a column that we never had before, right? Like what can you reuse at that point, right? You either have to assume some default value before, or you actually have to start a backfill. Like there are fundamental limits here, but most of the time people just want to like slowly evolve, add new views, things like this. For that, this should be more than sufficient.
Kind of like applying incremental view maintenance also to the application, right? Like you can grow incrementally. And that's actually very powerful for products that are really growing fast. They don't know what kind of queries I want to support like 6 months down the line, right? And that's really powerful. Okay, cool. I want to go into a little deeper from the architecture point of view. Okay, so I've written my tables, and data is coming in. What exactly, where does the partitioning happen? How is it decided? And let's start there, and then we can see.
So when you write the SQL and our compiler generates the DBSP based Rust program, at that level, if you look at the source, there's nothing about partitioning, right? Like you basically the tables and the data definition become structs, right? Like, so these are very compact representations. There's no sort of interpreting happening, right? Like we create a very specialized pipeline just for your pipeline, your use case, basically. These go into in DBSP what look like, map, join, like these type of operators. That's what you will see on the Rust program at the top. Behind the scenes, what happens is like DBSP is configured with a certain number of workers. Okay, so let's say I have 8 workers because I have a machine with, say, I don't know, some number of cores. Each worker runs an entire copy of that circuit, right? So it has the same copy that everyone else has of the circuit. And then internally, what happens is the data gets exchanged or resharded based on like the hash of the key that comes in, right? So that every worker is responsible for its partition of the input state, right? So if you have a join, for example, you might have there's typically an exchange before it where you have to shuffle it.
Yeah.
Now, what this pipeline does is like when you get these changes from this connectors, it basically accumulates them in a queue, and the pipeline is trying to like really pull as fast as possible from that queue. It operates internally, we call it batches. It's basically a set of Zsets, right? So a set of changes that's going through. Every operator takes an input batch and produces an output batch. So it's basically like a sorted array of rows, basically, right? And now, depending on what the operator does, internally it might need to look at indexes. Like a join operator would need to look at, like internal index that it maintains of the join. And these are LSM trees, basically.
Okay.
Yeah.
I think that's a simpler model, at least from the understanding perspective. Like, okay, you have the same pipeline running just on different partition of data. Partitioning is again done on the key, and the hash of the key.
Yep.
And let's talk a bit about the storage layer. Like you talked about indexes, right? Like, where is the data exactly stored? How does these the Rust binaries or the pipelines interact with the storage layer? And is it like decoupled, or is it like coupled within the pipeline? How does that work?
It is a co-designed storage layer. And we did actually investigate using things like RocksDB in the past, and it just didn't work at the performance point we were at. Right? Like we can typically do millions of events per second on a laptop.
Okay.
And there's some technical reasons for it, like having to do with like scalability across multiple threads, and also like serialization, deserialization, zero copy issues. Like there's a bunch of these things that the guys ran into. We've blogged about it. But basically, we have a co-designed storage layer. Since you asked about the, where these things get stored, like we can operate in memory or we can operate in storage. There's a backend thing you can configure when you create your pipeline. And so the way to think about this is that when, let's take the join again, right? So what is a join operator trying to do? It gets a set of deltas from, it doesn't matter where it got it from. Some other operator sends it some set of Z-sets, some deltas. And now it might need to look up which of these, like what is the change I need to compute to this join, right? So it does its part of that algorithm from we discussed earlier, but it needs to look up for each of these keys what is in the underlying index that it maintains, right? And so let's say some of the things matches, and it now knows that these new entries have to be recorded in the LSM tree. So in DBSP, we have foreground workers and background workers. The foreground workers are the ones evaluating the circuit operators, right? And so these things are meant to go as fast as possible. It's just doing time proportional to the amount of like the size of the delta, not the size of the database, right? So they are like zooming ahead, getting Z-sets. Where it matters, they have to do some lookups to the LSM tree. The nature of the lookup will depend on the operator, right? Like for example, the rolling window operator has to do something a little different from the join in terms of how it leverages the LSM tree. But ultimately, it does some lookups, and then it decides, okay, these are the changes I need to insert into this join, the LSM tree that's backing the join. So so it has to do a write after that. These writes are very efficient. It's just like a append-only type of operation to the LSM tree. The LSM tree itself is like, it's the typical, you have several levels, and we store these things called batches that I mentioned before. It's a group of Z-sets. It's a sorted array of the Zsets. When we use the storage backend, each of these is like a B tree, if I remember correctly, right? And so the foreground writes a batch. It's an append-only operation. It goes into the LSM tree. The background workers are constantly compacting these LSM trees, right? And so that is kind of like for most large workloads that we deal with, like where the size of these trees in total go into the terabytes, like that usually determines your performance because the foreground has to read LSM trees. So if you have too many unmerged batches, that's kind of, you have that read amplification to storage, right? Whereas the background workers are trying as fast as possible to compact these, so that ideally the number of reads you do is just one per level. And usually with Bloom filters, you can the amortized cost should be a lot lower than reading n levels.
Okay.
Right? So that is kind of what happens underneath.
Interesting.
Yeah.
So it's pretty much the standard LSM stuff, high level, right? You have multiple levels. Each level stores, sorted Zsets.
Yeah.
And then, there's background workers that are constantly compacting, so you don't grow your levels too much, or,
Exactly.
kind of uncompacted files, which may impact the query performance and so on. To skip some of the, let's say, files, you have Bloom filters. So again, pretty standard stuff.
Yeah.
And one typical problem I've seen, also with RocksDB LSM structure, is that the background workers who are doing the compaction can actually also impact the foreground workers, because resource consumption, depending on the spike performance and so on, it can happen. So is there some tuning there, some coordination between the background workers so they don't impact the foreground workers?
For sure, yes. This is something we've been actively investing in lately, like the tuning of the thing. Like ours is a bit of an interesting use case because the fast, like it's a dynamic system, right? And so like I'm getting like a lot of flashbacks from my PhD years on these type of problems. But basically, like the faster the foreground workers go in some of these operators, the more writes happen, which is more work for the background workers, right? And so we have back pressure mechanisms, we have all of this. But in general, like, there are workloads where you're mainly bottlenecked by, there will be some equilibrium state you hit where this is the speed at which the merge is operating, and therefore you're kind of stuck at some certain read amplification for some time, and that will determine your performance. So the other thing is that our background workers currently have to, they're not compacting one LSM tree, they're compacting all the LSM trees across all levels across all spines, and they have to like move across them, right? So there's obviously some tuning there. Like it's actually like a very classical scheduling problem, basically, like queuing and scheduling problem. Yeah. So there's some tuning there. Right now, what happens is each worker, it's like a cooperative scheduling type of setup where each background worker spends some number of credits worth of work merging a particular LSM tree. And if that's completed, it moves on to the next one, right? So there's obviously some tuning here, like how quickly do you jump between them? Like the more you jump between them, the more you will be kinder to smaller batches that need to be merged across trees. Whereas at the same time, like leaving something half merged also has no value, because like a merge is only useful once you've brought in something and produced an output batch so that the read amplification goes down. There's all kinds of balancing games here. We do multi-game merges, for example. So there's also a trade-off between compute and I/O there, right? Like sometimes it's actually better to wait for a few batches to accumulate so that you can merge them in one pass rather than doing that many pairwise merges. So yeah, definitely a lot of tuning to go.
Absolutely.
To go through.
It's a continuous work. It's not like, okay, this is going to work, that is going to work. You have to always tune based on the workload as well. That's cool. Now, okay, so far the streams are coming in. You're storing in LSM tree. Compaction is happening. All good. And when exactly is the view propagation happening? Like the view updates.
So the views are like, so we call it the synchronous compute model. And so the pipeline operates in these synchronous steps. So it's like a transaction basically, right?
Mm.
So in one step, it takes some Zsets to process to input tables, and then it evaluates the entire circuit. And only after it's done does it say, I'm done, at which point you can see all the deltas to all the views atomically.
Okay.
There's never an ambiguity in our case that some views are ahead of others, etc., which is again like a thing, if you ask me, that the stream processors got wrong, right? Like they went into this eventual consistency realm where you can't really make any sense of things across computations, and you have internal consistency problems, all of that. None of that. Like here, you'll basically, they always update atomically. Yeah. So you get the
Interesting.
full set of deltas to all views at the end of a step.
Okay.
Yeah.
I think the idea is that the step itself is so fast that it's worth the trade-off, right?
Exactly. Yeah.
Okay, so I think the Z set is like the unit of work that you have to do for each step, right? Like you take one Z set or you take a batch of Z sets. Okay,
It's
interesting.
always a batch. Yeah.
Interesting.
Like,
And
the
is
thing
there
that gets
any
is a batch. A batch is a like it's a certain array of
right?
C sets based. Yeah.
Okay, and then Z set is basically coming from this mathematical foundation that okay, interesting. What is the like a typical size of a Z set when we talk about regular stream processing workloads? Are there any recommendation? Are there any trade-offs between the sizing of the Z set, the batch size, and so on?
These are things that the user should not like. It's the user should not need to know about this at all. Like they should
Yeah,
not even need to know about Z sets. By the way,
yeah,
like you
yeah,
just
yeah.
write table and stuff like this, right? Internally, there's all kinds of things that show up. For example, like the Z set is really just a table and a weight column. That's it. So if you have very wide tables, that's the width of your Z set plus one extra weight column, right?
Yeah.
The number of things per batch is also like it's actually a configuration to DBSP. It depends on just how many you're pulling from that queue at a time,
Yeah.
right? So you can DBSP will let you take the entire data set and compute it in one step if you need to, but usually most people wouldn't want to do that, right? Like so, yeah. So there's some like there are, especially when you're dealing with things like recursive computations, for example, right? Depending on the problem you're applying Feldera to, it might be that your graph is so big that there is some amount to blow up. So you might like those are the kind of limits where you might need to care about sizing how many things get pulled into a given step, right? But most of the time, it's like this engine is so fast that you should not have to tune this. And and you pointed out correctly, if a step is fast enough, then you're just trying to do as much as you can in each
Right.
step. Yeah.
That is a good point. Yeah.
Yeah.
I mean, from the user perspective, like in probably most cases, they just have to understand their data model and the queries they want to run on, right?
Yeah.
And with this, I want to ask the other question, which is, I think you covered briefly that, at least in the SQL world, data model also drives performance, right? Like if I have a badly designed data model, like tables are not designed properly, it will impact my performance eventually, depending on the size of the data and the queries I'm trying to run. How is that in Feldera? If I create a data model which probably is not optimized, I don't know if it even makes sense for this workload, because optimization is taken care by the platform itself. But is there any dependency between the table structure and the optimization that you do?
Yeah, so it's interesting. So our performance model is actually quite different from what you would expect in a batch world, right? Like there are things that are considered like, for example, in the batch world, you'll see again, if you look at these DBT generated queries, you'll find them generating these monster queries. And there's probably a good performance reason to do that in the batch world. But in Feldera, we encourage you to write like views out of more other views, right? Like you break down complex computations into smaller ones and write small views so that you can actually build them up like Lego, right? You understand what this does, so you understand what these two do, and so on, right? Ultimately, like I said, the amount of work we do per step is determined by the size of the change. And it's not just size of the input changes, but also size of the intermediate work we're doing, right? And so there are, we've seen queries in the wild that um, do work that is not actually meaningful, and therefore you incur a performance hit. Like Feldera is still fast, but like you can get it much faster if you optimize it. For example, I think we saw a query once where someone was computing a count somewhere and much more downstream. And this is after like, I don't know, something like 150 left joins and unions and distings. And it's like a really complex query. And somewhere at the end of this, it was computing a count. And then again, further down, the only thing they were checking is that if that count is 0 or not.
Okay.
To filter some data. So what this means is in that pipeline, there's work we are doing where we are emitting deltas because of that count, because the count is changing every time any of these like gigantic joins are changing. So it's emitting a lot of deltas because of that count. But downstream, after that, nothing is happening. Like a few steps away, there's no value to that count other than is it 0 or not. And so a small rewrite there where you just check if something was, I think it was something like a left join is null or whatever, like some side of the join is null. That's all that was really checking.
Okay.
You make that small change and suddenly there's a lot, you recover that performance, right? But these are in the sort of, we are actually like investing in like, more user-friendly tools to see this happening without our input, right? Like today, like our users, we have a profiling API, so they can basically send this bundle to us, which graphs out the entire operator graph and gives us all the statistics about it. And we look at it like, okay, so what is this count? Was the first thing we asked. And then we looked at the query and like, yeah, okay, like this is not actually meaningful for you. So rewrite it into a where clause and suddenly that becomes much faster. But these are pathological extremes most of the time. They're
I
not,
mean, it doesn't happen regularly.
Yeah,
Right.
exactly.
Cool. And as you said, the platform is improving. So probably there will be a way to, kind of gives this warning that there might be a performance hit if you write this query, or there is an improvement, something like that. That's cool. Going back to the example, let's say for email analytics, especially from the email world, right? I've seen, you send an email and then you receive, after, I don't know, hours that, okay, it was bounced, right? And then, I don't know, because the inbox was full or, something like that. And then you get, probably there are retries, you get another event that, oh, it wasn't bounced, but it was, accepted. And then you get red receipts and so on. So the point I'm trying to make is, in our example, there are, let's say, there's a little delay in the events that are coming. And then, of course, they can also come out of order. And they can, they have this mutability that you have to update the state. So in typical world where, let's say, using Kafka Streams or Flink, I have this notion of, how I want to, if I have to do window aggregation, I have the notion of how I want to, address the out of order events or old late events and so on. How does that concern in Feldera, and what controls do the user have?
This is, I would say, one of our most differentiated features. Like we're the, again, only engine on the market that can tell you what lateness means, right? Like, so again, mathematically precise lateness implementation, basically. So if you take a pipeline without lateness, right, and you write views and stuff on it, in a way, Feldera always has to assume anything you've sent us can change. Right, like some record that like came in 3 years ago can be updated or deleted. We have to assume that, right? And so obviously, like again, there's at a fundamental level, IVM is about trading off time for space, right? Like go fast by keeping space, like indexes, so that you can compute deltas. And so in a pipeline without lateness, which actually a lot of our users do, by the way, because they want full materialization, you kind of have to keep a lot of stuff around. Even though it's very unlikely that all of it will change. Lateness is actually a way to do better than that. So with lateness, what you can do is you can take any input column in Feldera, like a timestamp column, but it also can just be an integer column. So we don't really distinguish there. But once you say lateness of a certain value, what it promises us is that you're telling us about a property of your data source that data will never arrive more out of order than that lateness value.
Mm-hmm.
So the easiest example is on a timestamp column. You say lateness, say, I don't know, 7 days, right?
Mm.
What this means is if I get like compared to the most recent value I've seen now, you will never see a value that's older than 7 days,
Mm-hmm.
right? Now, Feldera is, again, it's uniquely powerful here because we can tell you exactly what lateness means, and it's deterministic. It's not like some thread waking up at random times and doing stuff. It's always like you'll get the exact same result always, unlike with stream processors like Flink. You can define multiple lateness annotations across multiple columns, across multiple tables, but you can also define lateness on views.
Mm.
Right? Now, what we do with these lateness annotations is like we look at these indexes. These indexes are really integrals inside Feldera.
Mm.
And then we do what's called what is the term? I think it's called a forgetting filter, forgetting integral or something like this. Like Mihai recently gave a talk about it. But what it does is that it augments the circuit with some extra filters and some
Mm-hmm.
operators that compute what we call a watermark,
Mm-hmm.
which is basically, in some sense, a frontier for anything under this watermark is not going to affect the calculation of any of the views and therefore
Mm-hmm.
can be dropped. So against the circuit, there's like a watermarks that we compute on the side. So these watermarks then feed back into the integrals or the indexes that we're maintaining as a filter that lets us forget old state. That is not going to affect the output in any way. So we basically do static data and dynamic data flow analysis on this graph to inject these things, right? And so what the effect of it is, sort of to pop it back up. Let's say you're doing a window aggregation somewhere for
Mm-hmm.
30 days, let's say. The naive, so if that's the only thing before a lateness that comes after lateness annotation of, let's say, 7 days, Feldera will know for that window operator I only need to keep 30 plus 7 days
Mm.
worth of data, right? Because that's the out of orderness slack we have.
Mm-hmm.
But the real cool thing is that if you now do any kind of what's called a monotone transformation in your pipeline, deep inside, like, this might actually become something else. It might actually be 30 plus 2 days based on how
Mm.
what all intermediate views and stuff like that you have. And you can also put lateness on annotations on views themselves, right? But when you run a step of the pipeline, at the end of it, we know exactly what we can now garbage collect, which means you can now compute on unbounded streams of data with finite memory and storage.
Okay.
Yeah.
That's interesting.
I hope that makes
But
sense.
yeah, I think it did.
Yeah.
But it's a little still blurry because
Yeah.
I'm trying to compare it with, let's say, like watermark is also a concept in Flink, right? How is that different when it compares with Flink?
I think maybe I don't know which I think we call it a water line. They call it a watermark. It might be
Ah,
something.
okay.
And I think the distinction Mihai draws is like he could never find an actual explanation of how lateness and watermark, like, what is it supposed to do? Like, mathematically,
Hmm.
what it's supposed to do in Flink is never clear. And one complaint from our team was that you can never write a unit test in Flink
Hmm.
that can test the semantics of it because it's not clearly specified.
Hmm.
Whereas in Feldera, it's very clear. Like, at the end of a step, you know exactly what can be now garbage collected.
Okay.
Right? Like, what is late is well defined for us. Yeah.
Right.
Yeah.
No, I think that makes sense now. And do I also have so as a user, I just define the lateness, and
Yeah.
probably it like, I don't know, 30 days windows plus whatever lateness it is. So that's the minimum amount of data that it will store, right?
Yeah. Exactly.
Just to understand if lateness, is 7 days or not.
Yeah.
Do I also have the control to identify what events were late? And let's say, I mean, I don't know, there have been cases, at least in my experience, that we say that, I don't know, in our case, like 15 minutes and then 1 hour is the lateness. And
Yeah.
after that, any event doesn't make any sense, right? But then there are always like life happens, there are incidents, we made a bug, and then we are like, oh no, we need that data, right? And then instead of again like backfilling the entire topic or something and doing the whole process again, which might again be time
Yeah.
consuming and also error prone,
Yeah.
if I know what events were late, probably I can still process them. um or I don't know. So what is the like thing it is dealing with?
Yeah, this is a good question. I don't think you can do this today with Feldera, but I don't think it's not doable. Let's put it that way. Right? Like,
Okay.
currently, the implementation doesn't support it.
Yeah.
Lateness is I think there are. So one thing we are working on is this error stream, and we are evolving it. You could think of a world where late records show up there, and then you kind of decide, well, actually these things were fine.
Interesting.
Let them in or something like this, but I'm not sure how it will interact with the rest of the computation. There's probably some subtlety to take care of there.
Okay.
But yeah.
I think it's fair enough. And I was about to ask the next question, which is the error events, like the bad events and stuff like that. Because again, like my upstream can produce bad events because of a bug or some missing data and stuff like that, or just bad deployments.
Yeah.
And then I want like a mechanism where I can say that, okay, it's a DLQ, and then kind of reprocess them or do something manually. So I think the error states is a form of DLQ, right, in Feldera?
Yeah. So we're still hardening that side of the engine. It's actually well defined inside Feldera for operators to actually do the Rust equivalent of a result type, right? Where it either produces the correct result or it actually there's an error, and then you can go into the error stream, and if you resolve it, it actually it's actually the whole chain is well defined. We're still closing out that part. Similarly for panics, right?
Yeah.
In a batch world, you can run a SQL query. If it overflows, it can throw an error, and now that query didn't run. Right? This gets a bit. There's more of an operational implication in the IBM world for these type of things. Right? What do you want to do as a user? Do you want the whole pipeline to stall? Do you want to take a note and ignore that record and have other things progress? That's kind of a judgment the user has to make. Our goal is to give them the options there. Right? Do you want to stall? Do you want to because sometimes skipping the record might not also be the correct move, right? If it
That's
has
true.
cross dependencies.
Specifically in like financial domains and stuff like that, things really become hard. Okay. Like talking about like error scenarios and stuff like that, like late events. There are other failure scenarios, like I don't know, just system level problems or duplicate events, right? Like how do you maintain idempotency? Because all the view maintenance will depend on that. Of course, there is like a unique ID that I can define, but how is that done efficiently?
So Feldera supports primary keys. There's a few levels to this. Let me explain. Sometimes your data has quality issues, and there are duplicates where there shouldn't be. Right. You can address them through Feldera, right? Like you define primary keys, you make sure that's addressed. I guess if you use primary keys, it means we have to keep an index. Is my right? Ultimately, that's all we need to care about. And then, of course, you can do the SQL distinct statements as well. So you can address quality. People do usually use us to address quality issues as well. Like this, the early views usually do some cleanup of this nature compared to later views, which do the actual. So you asked about a few other error scenarios. What was it?
Yeah, so like idempotency, or like I don't know, a job fails, and how does it know that
All right.
where
Okay, so
exactly
for
to
this we
restart?
have so our enterprise version is fault tolerance, and so you can think about the so the connectors. So there's the connectors and there's the pipeline itself, right? Like I said, we have the LSM trees at the pipeline level.
Right.
We're constantly updating them, and you can periodically take a checkpoint. Meanwhile, the connectors maintain if you have fault tolerance enabled, they maintain a log. like a journal of their of the changes that they have, right? So those journals plus the checkpoint, there's always going to guarantee that you don't lose lose a write.
Okay.
Modulo us keeping those two things available, right? Like, so we currently spill to storage. We are about to release our S3 backend, in which case these things will be backed by S3 with the corresponding performance implication. Yeah.
Okay. Interesting.
So that means the result of it is that if you nuke the pipeline, as long as you can pick up that DBS volume or S3 bucket, you should not lose a write. Yeah.
Okay. No, I think that makes sense. And yeah, I think probably it's a pretty similar approach on how other systems also work. Like, I mean, nothing really new here, right?
Nothing
It's the
new here,
same
I would
problem.
say.
Like, yeah. Okay.
Same.
Interesting.
Yeah. Uh,
Let's take a step back, unless you want to add something more.
no, I was
Okay.
just gonna say, like, unless some things don't need reinventing, so
Right.
use
Right.
what
Right.
works. Right?
Absolutely.
Like, it's just standard algorithms here.
Absolutely.
Mhm.
I think let's take a step back and probably zoom out a little bit and understand from like at a very high level. So we understand like some of the basic differences between other platforms, like I don't know, Fling and traditional like combination of technologies where people write their own solutions to do incremental view maintenance. What if you have to kind of in bullet form, you have to list down few points about Feldera and its performance and the cost optimizations. What are the top three things that are differentiators for you?
The main thing, and I believe we remain unmatched here, is arbitrarily complex SQL, including regression with fixed points, right? And the guarantee that you can run it, or if you don't run it now, we can add it. We can confidently state that we can do it, right? There's performance, right? And I think usually like our storage layer becomes a differentiator, right? Compared to the alternatives. Then like the other stuff is really, like, I would say the bulk of these things is really just product type of
Right.
questions, right? Like, what's the user experience, onboarding, how easy is it to deploy, manage, operate? So that's stuff that we're continuously investing in based on use cases, right? Yeah.
Perfect. You briefly touched upon like you're working on some things, some improvements, but what is in the roadmap? And like not just about Feldera, but as the stream processing industry, where do you see the future is?
I actually believe that if you look at the world around us, right, take our day-to-days, right? Like every time we swipe a credit card somewhere, or we order a food item somewhere, or we close a card, or like these are all tiny changes to somewhere behind the scenes in some cloud somewhere, right? Like these are tiny changes to mostly unchanging data behind the scenes, right? And I don't think like the data infra that people have been using all these years with a lot of success, like Spark and Snowflake and things like this, they're not the right tools for computing on rapidly changing data, right? And so I see Feldera as basically solving that impedance mismatch between the kinds of data that people want to compute on versus the fundamental nature of how batch compute works, right? Like these things have to recompute from scratch. They don't know better. They don't have a concept of what has changed in your data, right? And that's what a Zset is at the end of the day, right? For us, it's a one representation from inputs to tables to views, changes to tables, changes to views, the journals. All of this is the same data structure for us, in and out, right?
Yeah.
This is kind of where we insert ourselves. And I think the main distinction from, I would say, like, so batch compute, obviously, like there's no concept of deltas and stuff like this. And so the other extreme is sort of discrete event stream processing, where they process one event at a time, right? Feldera, I would say, subsumes that whole range, with the caveat that like there's a fundamental nature to incremental view maintenance, that because you have to keep these indexes, your state can actually blow up, right? Like, so that I'm not going to hand wave that away. That is fundamental to this. But it does a better job at stream processing than stream processors. It does a better job at incrementally computing on like doing periodic queries compared to batch engines. And this is kind of how I look at the future going forward, right? Like IVM is more powerful than sort of this hodgepodge of tools that we've been using this whole time. So yeah,
Yeah.
so what people want are expressive power and the same ease of use
Right.
as a batch engine, right? It should just work. I think that's where we want to get to.
Absolutely. And I think like SQL is at the center of all of it. Like Flink has SQL, Kafka has SQL.
Yeah.
Of course, traditional relational databases have SQL. So I think SQL makes it really easy to kind of express really complex data flow graphs and results that I want, and without having all the complexities and um, so to say, like cost effective solutions. I think it's really powerful because you get best of both worlds, like good user experience and good performance. So that's really powerful, and I really wish you all the best in terms of the roadmap you're releasing, new features. And there's a very like a challenging space, but also amazing space where you can learn a lot, even for our viewers. I'm going to attach some of the resources that you shared with me earlier, but if there are more resources, learning more about Zsets, like really academic resources as well, please share it with me so I can attach it in the YouTube description, so people can view it and also learn more about how Feldera is performing, and the amazing benefits. So thanks a
Yeah.
lot for joining me today. Of course, it's such a vast topic. We could not go deep into each of
Yeah.
those. But yeah, we can probably jump back on another call later, talk about another areas, and do another episode. So thanks a lot.
Would love to. Yeah. And thanks for having me, Kaivalya. This was a fun conversation. Yeah. I love doing these deep dives. I regret that I don't get to do it enough in my day job. So
Likewise,
yeah.
that's why I started a podcast.
Thank
Cool.
you. Yeah.